this video, we'll be talking about 3 different kinds of heat capacity that you should know about. The first is simply called heat capacity, the second is specific heat capacity, and the third is molar heat capacity. Heat capacity, which is symbolized by the capital C, is the quantity of heat a body of matter absorbs or releases when it experiences a temperature change of 1 degree Celsius, and the units for this are joules degree Celsius. The formula for heat capacity is capital C equals Q divided by delta T, where capital C is the heat capacity, Q is the heat, and delta T is the change in temperature. Heat capacity is an extensive property, which means it's determined by the type and amount of the substance that absorbs or releases heat. For example, a large frying pan will have a larger heat capacity than a small frying pan will. More mass means more atoms present, so it takes more energy to make all of those atoms vibrate faster. Here's a simulation that illustrates this. We have 2 pieces, let's say they're of metal, and the lamps underneath them are giving off the same amount of energy at the same rate. We can see that the smaller sample on our left is heating up more quickly than the one on the right is. Because it is smaller, it has a lower heat capacity, and it takes less heat to raise its temperature. One of the limitations of heat capacity is that it depends on the size of the object and what the object is made of. So you'd basically have a different one for each object of each size and material. A more useful type of heat capacity is the specific heat capacity, which is denoted by a little c. Sometimes we'll refer to this as specific heat. Specific heat is the quantity of heat that's needed to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. Different substances have different specific heat capacities, and there are tables that we can use to look up the heat capacities of a specific substance. Specific heat capacity does not depend on how much of a substance there is, just what the substance is. Let's take a closer look at how specific heat capacity is expressed in an equation. C equals Q over M delta T. Notice that that is a little c, which stands for specific heat capacity. We have a Q, which is heat, and we have an M delta T in the denominator. That M stands for mass. So we've basically just taken the heat capacity equation and we have incorporated the mass into it. So now it doesn't matter how big our frying pan is, it only matters what it is made of. Sometimes the symbol for specific heat capacity has a little p subscript on it, just to tell us that it occurs at constant pressure. Here are a few things to know about specific heat capacity. First, it does not depend on mass. A big frying pan has the same specific heat capacity as a small frying pan that's made of the same material. Remember, mass is included in the equation. Specific heat varies with temperature, but not too much. For AB chemistry, we can assume that specific heat will not vary with temperature. Specific heat is different for different states of matter. For example, the specific heat is much higher for liquid water than it is for water vapor or ice. Because different substances have different specific heats, the transfer of a given amount of thermal energy is not going to produce the same temperature change in equal masses of matter with differing specific heat capacities. For example, 1 joule of heat will not produce the same temperature change in iron as it does in water. The larger the specific heat capacity, the greater the ability to absorb heat before the temperature increases by more than 1 degree Celsius. In other words, substances with larger specific heat capacities have lower changes in temperature with a given amount of heat. If you look at this simulation, we have 2 equally sized blocks of mystery substances. We know that the one on the right has a higher specific heat capacity than the one on the left. Assume that the lamps are giving off equal amounts of energy. We can see that the sample with the low specific heat capacity heats up more quickly than the one with the higher specific heat capacity. Have you ever been to a swimming pool and noticed that the sidewalk is much hotter than the water? Well, water has a very high specific heat capacity, much higher than the sidewalk does, so the water takes longer to heat up than the sidewalk does. So let's do a simple example problem. A piece of unknown metal weighs 348 grams. When the metal absorbs 6.64 kilojoules of heat, its temperature increases from 22.4 degrees Celsius to 43.6 degrees Celsius. Determine the specific heat of this metal, which might provide a clue as to its identity. When I'm given a problem like this, I like to break it up into pieces to better understand it. We are given that our mass is 348 grams. The amount of heat is 6.64 kilojoules. Let's convert that into joules, because those are the units we're going to need for heat capacity. We can calculate the change in temperature by taking the final temperature and subtracting the initial temperature from that. That's going to give us 21.2 degrees Celsius. Now, in order to find the specific heat, we will take our formula, C equals Q over M delta T, and we are going to put in our numbers and get out our calculator and solve. And our specific heat, or specific heat capacity, same thing, is 0.900 joules divided by grams degrees Celsius. Now, if we were to look this up in a table, we would find that this is very close to the specific heat for aluminum, 0.897 joules per gram degrees Celsius. So aluminum is probably what this is. We can rearrange this equation for specific heat capacity to determine how much heat is entering or leaving a substance. Just use algebra. So we start with C equals Q over M delta T, and we can arrange it to Q equals mass times specific heat times delta T, or Q equals MC delta T. Some people like to think of this as QMCAT. Now, taking a look at this equation, you should be able to see that if something is gaining thermal energy, if the final temperature is greater than the initial temperature, then Q will be positive. If a substance loses energy and the final temperature is less than the initial temperature, Q will be negative. Make sure you watch your units, because sometimes you'll be given the mass in kilograms and you're going to need to convert it into grams. Sometimes you might need to convert kilojoules to joules, but we need to end up with grams and we need to end up with joules, so convert accordingly. Here's another example. A flask containing 8.0 times 10 to the 2 grams of water is heated, and the temperature of the water increases from 21 degrees Celsius to 85 degrees Celsius. How much heat did the water absorb? Well, let's see what we've been given. We know our mass of water is 8.0 times 10 to the 2 grams. We can look up the specific heat for water in a table. It's 4.814 joules per gram degree Celsius. And we have our change in temperature. That's final temperature of 85 degrees Celsius minus initial of 21 degrees Celsius equals 64 degrees Celsius. Now we have to find Q. Well, we're just going to use our rearranged equation, Q equals MCAT. And we will put our numbers in, and when we crunch our numbers, we end up with 210,000 joules. This is a pretty big number, so we'll convert it to 210 kilojoules. Now, Q is positive because the temperature of the system, which in this situation is water, increased after it was heated. The last type of heat capacity is called molar heat capacity. It has the symbol C with a little m next to it. And this is the amount of heat required to raise the temperature of 1 mole of a substance by 1 degrees Celsius or Kelvin. And this is the equation for it. C subscript little m equals Q over mole delta T. And we could either write the word mole in there, or we could substitute N, which is the symbol for moles. You can also rearrange this equation to solve for the heat absorbed or given off. And you will get Q equals NC delta T. N cat? Okay, well, that works too. So here's an example. The molar heat capacity of tungsten is 24.2 joules per mole Kelvin. Calculate the energy as heat needed to increase the temperature of 0.40 moles of tungsten by 10 K. That's by 10 degrees in Kelvin. So let's write down what we've been given. We have the molar heat capacity of tungsten. That's 24.2 joules per mole Kelvin. Delta T is going to be 10 K. And we have 0.40 moles, and we want to find Q. So we're going to use Q equals NC delta T, Q equals N cat, and we are going to substitute in our numbers, and our answer is Q equals 96.8 joules. In summary, there are 3 types of heat capacity we will encounter. The one we will encounter most commonly is specific heat capacity or specific heat, because it depends only on the type of substance and not on the amount of it. The equation Q equals mc delta T can be used to help quantify the amount of heat energy that's transferred between 2 bodies. Molar heat capacity can be used if we know the amount of substance we have in terms of moles.